Okay, so we're gonna pick up where we left off last time. So last time we had loaded in a database that contains some statistics about coronavirus or information about coronavirus. Let me load this in really quick. And we talked about merging in theory, doing joins across tables, and we can see sort of a practical application of that here. So we have two different data sets, the coronavirus data set and a census data set. And so if you want to populate the same table with, or if you want to add extra information into, for example, the coronavirus database, we wanted to look at, for example, how the number of cases are correlated with, say, the population within a specific area. You have to put these together. And so what we did was to merge based off of the state and county codes. And so if we look in the code, if you'll remember, we do a left join. That is to say, we include all the data about the coronavirus. Okay. I added one extra line here with a function called complete cases, which will get rid of all the NAs. And so CV full is going to be our new merged database or data set that includes everything from coronavirus as well as the estimate of the population in each given county in 2015. One of the reasons why we do a left merge is actually that the state and county indexes only appears once in census, but it appears multiple times in coronavirus because you have multiple days showing the number of cases in each county. And so you will have repeated attributes of the county that stay fixed over time. So even though they're tracking across dates, in the cases, it's a static estimate of the population by county. Okay. So I think at the end of class, there was a question about how you could do sort of operations based on groups within a column. Okay, and so what does that mean? This is the equivalent of if you are pretty familiar or advanced in Excel and you've ever used something called a pivot table. One of the big strengths of data table and dplyr is the ability to operate across what's called groups, and this is a lot harder to do in the base version of R. So let's take a look at that. But before we jump into that, I need to talk a little bit about data table functionality. So in a data frame, in a data frame, we have basic operations that look something like this. So in data frame, when we talked about operations within the square, or not the square bracket, you have row column, where in the row you can perform filter operations and indexing operations, right? And so this is actually, so this actually should apply to both row and column. And so this was, putting like vectors of numbers or vectors of Booleans in row and in column to return specific rows and columns. And then you can manipulate specific entry, or you can manipulate the indexing operations by doing filters. So this is the whole, greater than, less than, or equal to, that returns a Boolean that will then give you specific rows that you want. So that's kind of a high level sort of general way I think about the functionality of things that you put in the square bracket. With data table, it's slightly different. They call this IJ functionality. That's kind of the formal functionality described by the people who created this this package. And in J, in addition to indexing and filter operations, you can manipulate data. Okay, so what does that mean? Let's show a couple quick examples. So one of the things that I'm going to try and do here is to reformat the date. So this is a character, and there actually is an additional data format that I didn't cover. I'm just realizing, and that is a date format. And so we can change it into a date by a pretty easy function. So I'll show that. So first I'll show how I would change that column, the date column, into a date format in a traditional data frame. So that would be something like this, right, where we take that column and then we're going to reassign it with this operation where you say as date. So similar to many of the like as dot numeric and as dot character, this will turn a vector into a date type if the formatting is correct, and you can specify the formatting as an option in as date. I won't go into that. You can look that up yourself in the help function if need be. So it looks something like this. So this is how you would change a column to a date format in data frame. So this actually would work if I were to just run that, but I'll show you some of the power of data table for manipulation of data in J. So here, now I am in my square bracket, and instead of doing an index or filter operation, I'm actually going to create new data. And so I want a column called date, and when I create a new column like this, this notation is essentially the same as what I'm doing here. But one of the nice things is that you'll notice a difference in that whenever I'm inside the square bracket for my data table, I can refer to columns names as objects. So there's no quotes around here, and I didn't need to specify that it's pulling from a specific data frame or data table. So it sort of just knows. So if I go ahead and run this, it'll change the format into a date. Oops. And we should be able to see that here. Yeah, and so this format is pretty interesting, right? So before, when we looked at this, it was a character. And you usually only get summary descriptions like this, min, mean, max, and quantiles or quartiles based off of numeric entries. But actually, it considers a date to be a sort of subset type of numeric. And so in this case, you do get min to max and this sort of summary. That's how you know that it's different. I mean, we can more sort of robustly check that with structure, and we should see that the date format is now in date instead of character. So this is, hopefully you guys can see that this is a pretty different way or different functionality from data frame, where you're only allowed to do indexing essentially, whereas here you can actually do data manipulation, and that's going to help for other functionality in data tables as well. I was looking through the coronavirus data set last night, and one of the things that I was looking at, actually, if I load this again, it should look slightly different. No, okay. Let's see. Yeah, okay. It's been when I did the as date, it sort of reorganized everything to do by date and by county. So last night when I was looking at the data, one of the things I wasn't exactly sure what cases meant, and what you can see here is that these are cumulative cases, not new cases per day, which is why you see sort of repeating values across time in a single county. And so one thing that I wanted to do was to also make a column of new cases. So I'm going to do that here, and I'm going to make a new column called new cases. This is actually a little bit more complicated, so don't worry too much about what I'm going to put here. This is just another sort of demonstration of doing this J type operation in data tables. When I think about doing any sort of operation, it's always good to think about what you're doing sort of in English and then formalizing that in code. So even if you don't know the code, you can sort of figure out what you want to do first in your mind. I think that's always a good approach too, especially as you're learning, or for the folks who are learning how to do programming. So if I want new cases, essentially what I want to do is I want to subtract one entry from the last entry, right? So then what you would see here is that there is like one new case of coronavirus on this date. On this date, it goes from 1 to 4, so it's 4 minus 1, so that's 3 more cases. And then here, it's 6 minus 4, so there'd be 2 cases. In this one, this would be 0 because 6 minus 6, 6 minus 6, so on and so forth. So you want to perform that operation for every for every county. The only issue is that you don't want to be doing that subtraction, say from Washakie, Wyoming to Autauga, Alabama, right? So you only want to do that operation within a county. And so there's some actually extra grouping mechanisms within data tables that let you do that. And so let's take a look at how to do that. Here, it's just the number of cases. So cases minus, if I were to basically shift everything up by 1, right? And so it'd be 4 minus 1, 6 minus 4. And so the way that you do that is through a function called shift. So again, don't worry too much about this function. This is doing essentially what I explained in English. Okay. There is actually one other thing that you can do in data table after I and J called grouping. And so this is, if I want to perform any operation in J by some group, you can specify here. So if I say by equals, let's see, what do I have here? By FIPS. Then what happens here is that all the operations in my J area, so in this case, the cases minus shift, it repeats this operation individually for every group of FIPS coding. And so that's how I can avoid doing these overlaps between counties. So if I go ahead and run this, I can now see new cases. Okay, so maybe it'll be, let me just do this, easier to see. FIPS date cases, new.cases. Okay. So here we can see it doing exactly what we wanted, right? And so it actually misses out on the first one because it doesn't know what to subtract before. So you actually end up getting 0 here. But for everything else, it'll work. So this is going to be slightly inaccurate based off of the first entry of the data. Anyways, you have new cases, 3 here, right? Going 1 to 4, going 4 to 6. You have 2 new cases, 6 to 6, 0 cases, 6 to 6, 0 cases. Okay, so that worked. That did what we wanted it to. Okay, and I'm going to start with showing some graphs now, and I'm going to talk about some fundamental things about visualizations that you should think about, some things specific to ggplot that you should think about. But in sort of the meantime, I'd like for you guys to think about in this data set, if there's anything specific that you want to see plotted, and then we can sort of work our way through how to do that sort of on the spot. So while I do this next part, you can think about what you want to ask. Okay. So let me actually go to a whiteboard. Okay. So when I think about visualization, uh, it's always important to think about what you have in the data and how you want to display it and what sort of makes the most sense. And some of that is going to come through experience, but a lot of that is I often find that for a lot of people, we think about, oh, I need to make I just need to make a scatter plot, or I need to make a bar plot, rather than sort of, oh, what's the best way to think about how to display the data that I have. And so it's important to sort of think through that process. When you have when you have a sort of really rich data set and you have lots of things to display, I think the best approach is to think about it in terms of dimensions. Okay, and so you know, traditionally I'll have some kind of x and some kind of y axis, but actually you could even have some sorts of data where you only have one dimension, and so so I'll give a quick example of that. That might be something like a histogram, where you have data points and then you're doing counts. So you're not explicitly making the counts, and technically that is sort of a second dimension, but it's one dimensional in the sense that, like, in your data set, you may not explicitly contain the counts in your data. It's just counting. The program itself can do the counting. Okay, but that's sort of as an aside. When I think about displaying x's versus y's, you can actually have lots of other data that contain attributes in other dimensions. And so typically, you know, if I think when I ask people how would you display data in 3 dimensions, usually you would say something like you would add an axis essentially, but that's actually a pretty poor way of doing visualization. It's hard to visualize from a 2-dimensional surface like a 3D object. And then what if I were to say, what if I wanted to add another dimension? You wouldn't be able to display like a 4D static image of adding another axis. But there are actually many other ways of adding dimensions. Okay, and so if I were to suppose I were to make a scatter plot like this, and this might be something like, well, okay, I mean, we can talk about our coronavirus example. So maybe this would be something like population and number of cases, okay? And each of these would be a county. And let's say I wanted to also be able to view, let's say, the income of the county. And so you could display the income on a separate one, and then you'd have kind of like a 3-dimensional scatter plot, but it would be hard to visualize. but there are much easier ways of doing this. So what are some other ways of displaying other dimensions? You could alter the size of the data points, right? And so small ones might be low income, and large ones might be high income. Size equals income. So that's another way of displaying another dimension. Let's see, you could also display dimensions. Say you wanted to do an additional dimension of a categorical variable. Let's say you wanted to show counties with let's say you had another variable with counties that have more than, let's say, one hospital per 10,000 and more than one hospital per 5,000, something like that. I'm just kind of making up data. So this would be a categorical variable by county. And you could add this other dimension into your chart via colors, right? And so maybe this would be red, and this would be blue, right? And I could have something like this. Okay, and so this figure here is showing four different dimensions already. And suppose you had this data for every country as well. We could continue to add more dimensions. So let me erase some of this to make some room. So there's functionality in ggplot that would let you sort of add via what's called facets for other countries. And so this might be like China, France, Germany, and you can do this automatically all from sort of one data set. So I'll put a link to a really nice tutorial about ggplot in the code in a moment, and so you guys will be able to access that. And so it's a nice sort of guide to look through that sort of goes step by step to build up charts. And I'm going to talk a little bit about that, but I'll give that link so that it'll be there will be additional resources to learn this sort of thing. One more quick aside before I get back to plotting in ggplot is talking about the format of the data. So the base functionality of plotting in R is kind of let's see, interesting. So and also when you think about plotting in Excel, you typically have your data organized in a sort of specific format. And so, okay, what am I talking about here? There are two different types of data formats called wide and long. And I think most people are more familiar with having data organized in what's called a long, or sorry, not long, a wide data set. Okay, and so this is, if I can give an example, this would be something like in the coronavirus database, it might be something like cases, county 1, county 2. Okay, hang on. Actually, I don't want this here. It would be date, county 3, and so on and so forth. And so on day 1, day 2, day 3, the number of cases that I observe in each county would be, 0, 1, 2, 3, something like this, right? And so these would specify the number of cases within each county across my dates. And the form of this data is called a wide data set because you've got everything organized across sort of a wide array of columns. One of the tricky things about manipulating this sort of data set, if I go back to here, in the counties, you want to be able to manipulate a dimension across a single column, and so if I were to include all the individual column data, or county data individually, you'd essentially have to be plugging in every county, which is why there's this handy other type of data structure or form of a data set known as long. Okay, and so what does this look like? It's just a reorganization of this data to look like essentially what we have: date, cases, county, in which case where you would have dates 1, 2, 3. The county would be county 1, like this. Okay, I see a question here. Can you repeat why manipulation is hard for a wide data set? Yeah. I might be going too fast here, but the whole idea is that I have to specify what to put into my plotting function. Okay. And if I separate each column individually, then I have to figure out some way of adding each of those columns individually. And so you'd have to say, add a Y for county 1, add a Y for county 2, and so on and so forth. Whereas in a long data set, it's just add a Y for each county, or add, I shouldn't say Y, it should be add a dimension for each county. So once I actually get to the ggplot example, hopefully this will be a little bit more clear. Okay, so we'll go ahead here. You can see that in this case, it's a trade-off, right? So I thin down the number of columns, but I now increase the number of rows because I'm repeating dates 1, 2, 3 many times, because I have to have dates 1, 2, 3 for each county. And so in this case, if I were to fill in, it would look like this. So these two tables are exactly the same. They're just formatted in different ways. And so I want to get folks more comfortable with this one on the right, because that's the better format for doing ggplotting. Yeah, and I think I haven't sort of really demonstrated the power of doing this yet, but doing it this way allows for a lot more sort of flexibility in manipulating some of the visualizations that we'll do. So I tend to think these days that the long tables are actually a much sort of better format for doing visualization. Okay, so let's jump back to our studio. Okay. So this is the link to the tutorial I was talking about with ggplot. If you're not familiar with it, it's nice. There's a really, really nice sort of comprehensive guide, and it really goes step by step. This is kind of my little guide structure for how you organize a ggplot. Again, this is for visualization. You initialize your ggplot at the top. You have this thing called geom, which specifies the type of visualization that you want to see. And then there's all this other stuff here that helps you manipulate portions of the plot. Essentially, it's to make it look, quote unquote, sort of pretty. And so these are things that you want to pay attention to once you're really sort of trying to make your graphic look the way that you want it to. But the most important is initializing it here. And I'll show an example of a facet in a second. So let's go ahead and actually make the plot that I drew out. Okay, so we'll start with the basic structure here. So ggplot. The plot that I had made was a scatter plot, and the one that the way you do that is with something called geom point. You can actually have multiple. You can have like multiple sorts of what is this called? Like a not visualization. You can have multiple different types of these displays on a single plot, and so that might be if I draw really quick. Okay, I don't want red. Hang on. So that might be something like in a plot with x, y, if I want to do both points and a line. So the line would be one object, and the points would be a sort of different object. And you can have multiple of these things by doing something like this. It's a little bit more advanced to do this properly, I would say. You typically, for I would say when you're starting to do this, I would avoid trying to include multiple things, because you run into, because often what you end up doing is like adding a secondary axis, which is typically bad practice. Um, the reason why I'm bringing this up is because what I'm going to show you is, um, in the initialization, typically this is where you include uh, two main things, the data input and then the aesthetics input. So I see a question from Gene. Does the geom line function accomplish the goal of adding a trend line for the scatter plot? No, it does not. Geom line, you have to, you're specifying essentially all the points of the line. If you want to build a trend line, you can do something different, like I think it's called geom AB line, where you specify the intercept and the slope, or you would calculate the line and add it in as a separate data thing. Okay, so in this case, I'm gonna put in, oh my gosh, I forgot to do one thing. Okay, sorry, I feel like I'm jumping around a lot, but actually before I can show, before I can do the plot, which I showed by drawing it out, we have to do a little bit more data manipulation, right? So if I look at this data, yeah, I'll jump back to the ggplot in a second. If I look at this data, one of the issues is that if I want to show the total by county, these are showing it by every date, and so that's not what we want, because we're not actually plotting something over time in this particular example. So what I'm going to do is I'm going to make a new table called by county, and we're going to do a little bit more data manipulation, and I'm going to show in the J area of the data data table, I'm going to make a new column called total cases. Actually, let's do it two ways. Let's do total cases by sum, and we'll have a total cases by max, because we have, so what I want to do is get the cumulative cases by county and just ignore the dates, okay? So there's two ways I can do that. I can take the maximum of cases, right, which is giving already the cumulative one, and I just want the last one, and I want the maximum of the cases for every FIPS group, or I can add up all the new cases, and it should give me almost the same, not quite the same, because remember it's missing the first entry. So it's pretty simple here. All I need to do is say I want to add all the cases up. So new.cases, so that's sum of new.cases, and then I want, in cases, I want the max of this. So max of cases. And we're going to do that by every FIPS. And I also actually want to include, state information and population estimate. So it's going to do it. So technically, the population estimate is going to be the same for every FIPS, and the state is also going to be the same for every FIPS. So it's just so that I can add a little bit more data into here. Yeah, please let me know if this is confusing. I'm probably going through this pretty quickly. But here, what we've done is now extracted from the data table, the previous data table, a new data table where I have every FIPS individually, population estimate, and then the total cases. These should technically align, but like I said, there's like a slight issue where it's not including the first one. And so there's a slight difference. So this one is going to be more accurate, but I just want to demonstrate that we can do it 2 different ways with that data set. Okay, so let's go back to here. So in this case, CV by county, that's the data that we're going to be drawing from. And then the aesthetics is pretty straightforward. I can do, okay, what do I want on my x-axis? I want my population estimate. And on my y-axis, I want let's do the total cases by max, because we said that's more accurate. Okay, and here actually, if you can actually include all of this information inside the point instead of up here, and that will do the same thing. The main reason I do it up here is that, okay, so everything in the main initialization will get passed into all of your geom points unless you specify otherwise. So if I wanted to add like a trend line or some kind of line based off some other data set, I would explicitly say here, other data set, and then you would do the same sort of thing, like that. And now this will look at another data set to put in that information and plot it. But we're not going to do that. And I'm going to not go into that in any more detail. I'll let folks sort of look up how to do multiple geoms in the tutorial. Okay, so I'm going to run this, and we're going to see what happens. Should show up here. Yeah, okay, great. Yeah, and so here is sort of our first example of a visualization and how you do it. Pretty sort of straightforward, I think. And this is the basic structure that you need to do all of the visualization, and everything now gets sort of layered on top. And so I'll just quickly show some easy functionality or common functionality to add to here. So if I want to relabel my x-axis, it's just x label. So this is going to be population. On the y-axis, this will be cumulative cases of coronavirus. And then one that I basically always use, there are a couple different themes for coloring, and I use this thing, theme BW, black and white. It gets rid of the grayscale. So let's see what this looks like. Oops. Oops, let's see, theme BW. Here we go, one more time. Yeah, so it gets rid of the grayscale, adds these gray grid lines, it adds like a black box around. So that's all the stuff that theme BW does. But then I've also changed my x-axis to population, and I've changed cumulative cases of coronavirus. Okay, one of the things that I notice about this chart is that you have a lot of density of points here, and there's a lot of variation across this sort of large range. So one of the things that I quickly looked at was to do a log of both sides to help differentiate points within and distribute the points more evenly. This is just kind of for visualization purposes. We're not doing any sort of analysis or anything. I think it makes it look a little bit clearer. And you can see that there's, when you do the log versus log, there's like a pretty nice sort of correlation between population and number of cases. It's a lot easier to sort of see. Okay. So I see a question is, okay. So let me just type this out as a comment. Are these two things the same? So this is one of the slight differences in data tables versus data frames. So notice I'm denoting F and T as a difference between a data table and a data frame. So we learned in data frame that you do this you do this sort of notation. You do this sort of notation to call up specific columns in a data frame. In a data table, you don't have quotes, and you use list instead. And then this dot, I think I mentioned this last time, is just an abbreviation, so you don't have to type list every time. So these two will be exactly the same. And functionally, this versus this is doing the same sort of thing for data frame versus data table. So if you are in a data table, oh, I can't actually remember if this, so okay, I can quickly look. So if I do cv dot full date, so does this work? It does. So it's backwards compatible. In a data table, you can still do this. And that will be the same as cv.full of doing this. Yeah, but you cannot do data table operations on a data frame. And so if you're trying to do this with a data frame, it won't work. So hopefully that clears up the confusion there. Okay, so there's a question, what's the difference between a data table and a data frame? Okay, so the data frame is R's default sort of table that it stores. And the data table is an add-on package that adds a lot more functionality and actually speed and processing to the data frame inherent in it. And so I have transitioned to data tables because it allows for a lot of operations such as group by. That all the stuff that we've been covering today is possible to do in data tables, but not in data frames, or it'd be a lot harder. Okay, let's see. There's a question thinking about plotting. Excel has Power Pivot and Power View tools, and you can pass data from R to Excel. Do you think there's cases where it's more convenient to use Excel? Actually, I don't think so. I actually think that so I'm pretty familiar with doing plots in both programs, and at a certain point, I think the customizability of something like ggplot makes it way easier to manipulate, especially when we add extra dimensions. So there's there's kind of like, there's definitely an initial sort of learning curve to do some of this stuff. But I think as you get more and more comfortable and familiar with the functionality here, you're going to find that it's like way easier to do certain types of plotting programmatically than to do it sort of manually in Excel. And so I'm going to encourage folks to learn this way, and at least, you know, at least if you're good at both, then you can sort of choose, right? But if you only know one, then you're sort of pigeonholed into doing it one way. There are super easy ways of like quickly being able to manipulate data in here. So okay, I can even show, let's just go ahead and do something like this. Let's say I want to just plot this by state. In Excel, you would have to individually make each of the plot. Well, okay, there are some advanced ways of doing this, but actually, once you get there in Excel, it takes a lot more individual learning effort, whereas here it's applicable pretty easily. So what I want to show is, let's see, let's break this out by every state. Faceting creates new sort of facet windows. You'll see what it looks like in just a second. And let's see, I want to do equals free y. So I'm not going to talk again here about exactly what's going on. You can kind of learn this on your own, but I want to show some of the possible functionality that you can do. Hopefully this isn't going to be too crazy. Okay, so here it is a little bit crazy. I can plot individually a couple, all the states. Let me actually, just for the purposes of this, let's just do a couple states. Let's do states in California, New York, let's say Michigan and Texas, just so we can see it a little bit easier. Cool. So we can see what the trend looks like here. And let's see, if I wanted to add another dimension via size, just as a quick demonstration of how easy it is to do that. Let me see, I haven't prepped the data table to do that. I wonder, let's see, in here, if there's, I actually don't know what these columns are. Natural ink. Okay, that doesn't look like income because that's because there's some negative number. But okay, let's just do that anyways. Natural ink 2015. Even though I actually have no idea what that is, if we want to add that as another dimension, I can do that real quickly. I'm going to add that in here, and then in the county one, include that here. Okay, so if I want to add another dimension based off of one of the ones that I was saying, right, size, and so size is equal to, let's see, Natural Inc. 2015. Okay, and you can see I've been able to add pretty easily another sort of dimension, even if even if I don't actually know what this is. Okay, so that's a sort of quick set of high level overviews of some capabilities of ggplot. So I'm gonna stop here actually, because for showing the ggplot stuff, even though I asked to think about, if we have time, we can come back to this, and I can make a couple more plots that folks find interesting. But I do want to dive ahead into starting to talk about non-R related stuff.
Can I ask a question?
Yeah, go ahead.
Oh, so I have a question in the data manipulation up at the CV by county code.
Okay. Yep.
So in your group by functionality here, you grouped it by FIPS state and population estimate and the natural inc.
Yeah.
But I wonder if we're just graphing like the number of cases versus population in each county or state, could we just group it by either like any one of like either FIPS or state?
Yeah, I mean, you can group by. I could get rid of all of this. Well, okay, I need. Maybe it's better to put this over here because they're all the same. But generally, yeah, if I understand what you're asking, you can choose whatever it is that you want to group by. And I've explicitly pulled out all the items that I need for doing this sort of graphing, right? So I have the cases, population, natural inc, and then FIPS and state. If I didn't want to include the state information, I wouldn't need to include that here.
Gotcha. Okay, so it depends on what you like to graph later in the ggplot.
Yeah, exactly.
Okay, perfect. Thank you.
Yeah, and that's the sort of thing where you want to think first about what it is that you want to plot, figure out how you get the data organized, and then figure out how to do that, how to plot that. What I would not do is look at the data and say, okay, I just want to start making plots and arbitrarily do that, and then have to figure out, oh wait, I need to like manipulate the data the so and so way. Think about what it is you want to do first, and then organize in your head step by step, sort of like what it is you need to do for like getting the data that you need to plot it, and then how you would actually execute the plot in code. Okay. So let's start our first lesson about data analysis. So let me jump on over to the whiteboard. Okay. So when we talk about regression, we are generally presented with the sort of following type of function. So we have y is f of x plus some error term. And this essentially is figuring out the relationship between x's and y's. And so really what we want to learn about is f. Okay. In different fields of regression and data analysis, we're concerned with sort of different aspects of this relationship. In statistics and machine learning, oftentimes we care a lot about prediction. And that is to say that if I were to extrapolate values of x's or be given some values of x's, I want to be able to estimate my y's to the greatest sort of most accurate extent possible. In other sorts of fields where you have econometrics, for example, they care much more about causal relationships and causality. And so this is how my inputs will affect my output. Okay, and so there's an important distinction here in that the difference between these two can initially be sort of subtle, but it spawns sort of a whole sort of set of field of approaches and work and different methods of doing sorts of regression and data analysis. And so you could actually imagine that in more prediction-based methods, I care a lot less about whether X leads to Y. So you may see some sorts of incidents happen that aren't necessarily causally related, but give you good predictions. And you might be able to do better predictions by throwing in lots of variables, even if the variables themselves are like correlated. Whereas in models where we're concerned more about causality, you would have you would want to focus on variables that you know directly lead to a specific outcome. And so we'll get into sort of details of both of these in sort of a practical sense. And so there will be certain lectures that will be dedicated to different approaches across different fields. And what I hope to introduce in this course is a sort of good understanding from an applied sense of how to approach both of these types of data analysis. Okay, so what is regression? This is modeling the relationship between variables. Okay. So let me go ahead and pose this question to the class. Okay. Normally when I would do this in person, I would have different people come up here and draw lines of best fit. I think if anyone wants to have a go at this, I don't actually know how well this will work, but all of you guys who are listening right now, I think you might be able to do annotations. Is that right? Are people able to draw on this whiteboard?
I'm not sure because it's your share screen, so I'm not sure if we can do anything.
Okay, because when I draw on when I'm drawing on top of the RStudio, that's like from a different line. Oh, okay, great. Actually, so okay, people are actually able to draw. I see something. Okay, so what I'm going to ask you to do, whoever is doing that, okay, let me get rid of a couple of those lines, or actually, if I guess I can actually control your lines. So folks who are able to, and we don't need everyone to do this, but go ahead and draw a best fit line, and different people can draw lines. I'm hoping that what we're seeing is not your actual interpretation of a best fit line, because it's like way off, right? Well, are people seeing that it's like way up in the corner here?
Yeah, I think when you annotate it, it like pushes it up after you draw it.
Oh, okay, I see. All right, okay. Okay. So basically, I see. Basically, we see a bunch of different lines going like this, like this. Okay. So let me pose a question then. Which one of these lines is the best? And how can I tell? Is it the blue line, the red line? Is it the green line? Anyone have any thoughts about this? Go ahead.
Would we have to do some study of the errors between the lines and the points? Basically, I guess that's the mathematical approach to it.
Yeah, sure. That's exactly right. And so I think for a lot of you who have taken statistics class or an econometrics class, when we talk about linear regression, in drawing a straight line, the way that we sort of objectively say, oh, I think I can figure out what the best line is. Let's say I do the red one first. I can take the difference between my line and each of these points. Okay. And I can compare that against, say, the difference between each of these points and my blue line, right? And oops. And if I add, oh yeah, sorry, go ahead.
Question. Is it the difference, like the vertical difference, or is it the total difference? Like, should the lines that represent your error be perpendicular to the the regression line?
Yeah. Good question. Why don't we do that as well? So let's have like a perpendicular type of thing, like this. So which is it better to do a vertical line or a perpendicular line? What do you guys think?
I would think perpendicular.
Okay.
Wouldn't it be vertical because it's like a fixed y value? And that's what the difference is between the y would be the.
Yeah,
I
exactly.
guess vertical just because you want the shortest distance between the line and the point.
Yes, so the perpendicular would make it a little bit longer, and I guess the reason, I think one of the practical reasons for doing it is it makes sense to do the vertical because you're manipulating uncertainty only in the y, not in the x, right? Because the x's are fixed inputs. Okay, and so that's, I think, part of the justification of why we do vertical, although it wouldn't necessarily be wrong to do it as perpendicular. It would just be sort of a different metric, right? And so when I'm talking about here, looking at the vertical difference is one approach in understanding, or one metric with which we decide to say one line is sort of like better than another line. Okay. And actually, one thing to note is that when you do this, you could actually be canceling out values, right? So if this is like +3 and this is -2, it's actually going to decrease that distance, even if they're off by a lot, right? And so if I were to have, let me actually just draw a new plot really quick. If I were to have points like, actually, I'll just do the same color to demonstrate my point. If I were to do something like this, the sum of the differences between this one and this one, if this is +3 and -3, then in this one was +1 and -1, the sum of those differences is the same, even though we might say something about how the blue line is more accurate. And so the way that you deal with this, if folks are familiar with linear regression, is that we do the square of the difference. So just for sort of notation's sake, oops, let me change to black. So y, so the difference between here and here is y minus y hat. So I for every individual point. Y hat is our predicted. So this is hat, and this is a predicted value. And if you've ever heard of OLS, or ordinary least squares regression, which is the typical linear regression that you learn, that what that is doing is it's minimize the sum for all my i's, for all I, yi. This is kind of my objective function of a linear regression, and that's going to produce a straight line that reduces the difference between my points and my line. Really quickly, I'm gonna draw a line that is gonna beat all of your guys's predicted lines based off of this sort of based off of our metric of what constitutes the best line, which is the difference in distance between our predicted line and the actual points. Okay, so I'm going to draw it in yellow. So this line right here will be better than all of your lines when it comes to this metric. And so this is, it's one thing to start to think about as we think about fitting sort of functions to points. And obviously, I've made this sort of blatant example where I'm not using a straight line, although I did actually see an example of that, of people drawing that, not a straight line. And in this case, I'm reducing the distance between my points to a greater extent. But there are probably some issues that you're thinking about with how I've approached it with this yellow line versus what you're doing with a straight line. And we'll talk about some of those issues more formally of why it may make more or less sense to do a sort of approach with what I'm doing with the yellow line versus drawing a straight line. But that'll be a lesson for a different day. One quick question for, especially for those who have actually already taken a statistics class. One of the things that you might have taken for granted is like, what I'm trying to do is build up these steps about why we actually decide, or how we decide to choose a sort of metric, for a standardized metric for measuring the best reduction in error, right? Which is this y minus y hat for something like linear regression. So does anyone actually know the reason for why we do squared as opposed to what's a different way I might be able to get around the issue that I've shown here with the +3 -3? Can anyone think of a different approach to do it? Yeah, okay, an absolute value. That's right. So a bunch of people chimed in. Great. So does anyone know why we don't do absolute value as opposed to just doing a square? So it's actually entirely an artifact of computing power. Yeah, so it's, I see Vishnu message me, but I think in privately. So it's numerically much harder to compute an absolute value. Well, these days it actually be really straightforward. It's still numerically harder to compute, but you can just do it on a computer, and that's not really a problem. But back then, when regressions were first starting to be applied, and you had to do these things by hand, the square, solving this optimization with a squared term instead of an absolute value turns out to be much easier to do, because, right, so for those who are familiar with optimizations, it's a convex optimization, and you actually have closed form analytical solutions, whereas with absolute values you have this kink, and it makes it much harder to compute. So I think part of me talking about this is like thinking about things that you may have sort of taken for granted, and reasons for why that is. I mean, really the only reason why we do squared instead of an absolute value is an artifact of computational issues. But it wouldn't be any more or less wrong to say absolute value instead of doing the square, and that can actually change the answers that you're getting. So you should be aware to like take a lot of the assumptions of how the modeling happens with a grain of salt, because there are some assumptions ingrained in there that are often not talked about as much. One of the nice things of the form of linear regression that we have now is that there is analytical methods. And so an analytical method refers to a sort of solved optimization. And so the solution is much easier and faster, as opposed to numerical methods where you're iteratively doing what I would call sort of quote unquote smart guessing and checking of values. Okay, so let me go to a new whiteboard. So this is exactly right. As we talk about fitting a straight line through all these points, I'm going to do this. And then I can figure out essentially what the best line is to draw that will exactly create the smallest error term. So I can minimize this error term and figure out what this line is, and the properties of this line are commonly sort of shown as this. So yi is equal to beta xi plus alpha plus epsilon I. Okay. So you may be familiar with this equation, but just to get everyone on the same page, if you ever seen something like this or something like this, the M and the A refer to the slope, which is what your beta is. So this is the slope of my function. This is my intercept. And so that will define the properties of the line. There is an additional term here, which is your error term that gets you to your exact value. So yi, so I refers to an index for every point, okay? So actually I'll do it in a different color so that we can be exactly clear what this is. So this, if this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, something like that, I can look at my value of y1, which is equal to my beta x1 plus alpha. So this describes the point on the line, right here. And then I have to add my error term here, so epsilon 1, which would be the distance between my dot and my x. Okay, and so that's how I arrive at the actual point y1. And then y hat I is equal to beta xi plus alpha. And in this case, you notice that this does not contain my error value. No error term. Because the y hat refers to the predicted point. Okay, and so if I want to do, say, y hat of 10, that's equal to beta x10 plus alpha, that'll give me the point on the line, and this is exactly what I'm interested in, right? So this is my whole y hat function. And so that's, be careful of the notation between your y and your y hat. Okay. Are there any questions? If not, we're going to go ahead and jump back to R and talk about implementation of some of this stuff that we're just covering. Okay. Okay. Let us create an example regression model. So what I'm going to do is I'm going to create a quick data set here. Our UNIF is, for those who need a quick refresher, I'm drawing out of a hat a random number from a uniform distribution between 0 and 50. And I'm doing 100 draws from it. And then what I'm going to do is I'm going to have another term here called deviation, which is going to be from a normal distribution with a mean of 0, standard deviation of 5. I'm going to do 100 draws from that. Okay. And I'm going to create I'm going to create a set of points for y. Okay, and so here I have randomly generated points of x. And then there's going to be some error term that I'm making called deviation. And then I'm going to create artificially a set of y's that are based off of the half of the value of x plus some amount of deviation. Let's see. So I'm going to make that, and then actually I'm going to go ahead and put that into a data table where x is equal to x and y is equal to y. So let's see what that looks like. So for model.1, so I've got a whole set of points here. Okay, and let's plot this. Actually, all my notes are in the old way because I don't use, as I was mentioning before, I don't usually do ggplot because for these examples because it's a little faster. But we're gonna be consistent, and we're gonna do everything in ggplot. So bear with me. Hopefully this all works. Okay, so let's quickly take a look. So here is our scatter plot that I generated. These are all sort of, again, randomly generated points. And the way that we conduct a regression is via a function called LM. So I'm not going to get into the theory about how exactly how the values are generated. So when I'm talking about the values, I'm talking about the betas and the alphas. We may talk about that a little bit in another class, but for now, basically, all you have to know is that behind the scenes, it's conducting this optimization where it finds it's basically identifying a line that's going to reduce that error term. And if it's a linear function, it's always guaranteed to provide sort of the best solution. Okay, so example, actually I'm going to do this up here. Example model 1. It's going to be y regressed on x. Data is from for model 1. Okay, and so this right here, this is my response variable, and x is my explanatory variable. There are other terms for this. Sometimes you may hear y being referred to as a dependent variable and x as an independent variable. I tend to try and avoid that nomenclature because it overlaps with a statistical definition of independent versus dependent, which are definitely not the same. And so to avoid any of that confusion, we'll do our best to call them response variable and explanatory variables, which are the corresponding to dependent variable and independent variable. Okay, so I'll go ahead and run this. And we can see the results of this. And actually, if you type summary, I think it's a little bit easier to read and it gives a little bit more details as well. Okay. So let's see. Here, in the we actually are able to know the true function, right? Our true function is y is equal to 0.5 times x. And here, the way that you would read this table is the alpha is the intercept here. And there's actually no alpha here, it's 0. And it's estimating, our best estimate for this line is an intercept of negative 0.49, 0.487, and so on. And x is 0.47965, as opposed to being 0.5. So it's not an exact estimate, okay? Because we've got noise contained in here, there's some randomness associated with this, so that the estimate that's being provided by this linear model is not always going to be exactly on the true value. And so what they do is they give some standard error. And so, you know, I think when it comes to interpretation of a regression, you know, some of the things that people just look at is like, okay, you know, there's a significance of, you know, at 1% or 0.01% or 0.1% or whatever it is, and therefore I believe in my regression, and these estimates are great. But really, you should take the time to think about what it is exactly that these estimates are telling you, right? And so if I were to just sort of read the table in a way that I think a lot of people do, and they say, okay, here's my estimate, it's statistically significant, and so this estimate is like an accurate representation of what the real value is, even though I can really easily kind of look here and say, I know what the true value is, it's 0.5, and that's not what the estimate is telling me. And so what these standard errors are telling you is that it's most likely within some amount, some error of my estimate. I think that the true value of my of this coefficient is within 0.03623 from my coefficient some percent of the time, right? And so these are normally distributed, which means that there's the what is it, 67% rule, 95% rule, and 99% rule, something like that. So 95% of the time, my true value will be within this estimate of the standard error. Okay, and that is the sort of formal definition that I think folks should keep in their mind when trying to do interpretation of results, and not just say, oh, my model is good because I have statistical significance. The other metric that folks commonly talk about with how good a model is the R squared, which is this value here. And so you may have heard of that. And when you talk about it in your statistics class, what they'll describe is that the R squared describes, right, the variation in the variation of the data that's captured by the model. So let me write that out real quick. So the formal definition of R squared is equal to 1 minus the sum of, okay, this might get a little messy. So let's go to a shared screen or the whiteboard. Okay, I see a question. Does t-value and PR have any significance for interpretation? Yeah. Okay, I should talk about that real quick. Yeah. So these the t-value and the probability are describing whether or not my estimate is different from 0. And that's actually having to do with interpretation and the significance too. And so the significance actually doesn't describe anything about the accuracy of your coefficient. It's actually just describing whether the likelihood that your coefficient is a value not equal to 0. So this is the standard error of my estimate. So it's saying, right, the estimate should, within some percent of the time, be contained within some bounds of the standard error. And we'll talk about confidence intervals and what all of that, what that means. The t-value refers to the number of standard errors it takes for you to get to 0. So this says there's about 13.239. So if I multiply this number by this number, it should equal the estimate. And the chances that the estimate is that far off from 0, which is saying that it's different from 0, it's not a 0 value, is this probability. So in this case, we said that there's no intercept, and this is actually saying, yeah, well, my estimate is this, but 63% of the time, my estimate is going to be 0 or actually greater in this case. And so you may actually say in the interpretation of this, the difference from 0 is not statistically significant, and so I might say that there's a 0 value for the intercept. So that's what the t-value and the probabilities are referring to. Let's see. Turn this off, go back to my whiteboard. Just really quickly for your reference, and obviously you can also look this up. R squared is equal to 1 minus the sum of yi minus yi hat squared. So that's my the sum of all the error terms, also known as residuals, which we'll talk about later. Minus the mean value. Okay, and so essentially, okay, wait, I see a question. Should residual standard error be similar to the square root of 5, since 5 is the variance of error? Actually, I'm not quite sure I follow that question. So there is, let me see, I don't know the equation off the top of my head, do I? I do have it in my notes. So if you want to calculate the standard error, it looks something like this. So again, I'll write this as reference, but it's not, oops, not square, sorry. It's not something that you need to memorize or anything. Okay, so this is the equation for a standard error where n are your degrees of freedom, which refers to the number of parameters in your model. So that's like the number of betas and number of alphas. Yeah. So in this case, so again, looking at Lisa's question, it's not like a set value like 5 because it's going to depend on the data and on the number of parameters in the model. So hopefully, if you refer to this equation, maybe that'll clarify that question. So really quickly, just to, I'm running out of time here, and there's a couple more things I want to show. So I'm going to quickly show for R squared, essentially, what R squared is essentially showing qualitatively is that I have a set of points here and I have a best fit line. Okay, and I can figure out the errors up here, and then what this bottom denominator is showing is the difference with the mean value of y. Okay, and so what that is if I take the average of all my points and I just plot them, or the average across the y's, nothing to do with the x's, and I plot like that, what you'll see is that I have one set of errors which are in the numerator, of the r squared, and then I have another set of errors which are in the denominator of my r squared, and it's essentially looking at the how good is my model compared to just a flat line that averages across all the values, and that's strictly what the r squared is referring to. And so I think oftentimes people, oftentimes folks will look at regression models and will think about r squared and standard errors as like the main sort of metrics of success of a model and how good a model is. But they mean pretty specific things, and it's not an end-all be-all of it's not an end-all be-all of how good a model is. And in fact, you know, the r squared and the standard errors, oftentimes people will extend the interpretation of what they mean to beyond what they're supposed to be sort of describing. And so I want to show an example of this. Let me bring this up real quick. There is a unique data set. Hopefully you guys haven't seen this before. It's called the Anscombe Quartet, and it was a specially designed data set to sort of demonstrate the point that I'm talking about here. Yeah, for purposes of time, I'm not going to change these into like data tables and into ggplot. But that's all right. That's kind of independent of the point that I'm trying to make here. Okay, so there's within this data set, there are 4 groups of y's and x's, and I've run a model against each of these, and I'm keeping them hidden from you guys sort of on purpose. But instead, what we're going to look at is the linear fit between each of these 4 sets of y's and x's, and they are different data points. Okay, they're not the same. And let's quickly sort of go through them and interpret them. Here we have x1. It has a beta of 0.5, and it is statistically significant to the 1% level. It's got these 2 stars. Yeah, and it's got an intercept at about 3. And our r squared is 0.66667. Okay, and so that's our findings from our first linear model, is demonstrating this. Let's take a look at the second model. Okay, again, we have an intercept of 3. We have 0.5 for our estimate. We're significant to the 10% level, and our r squared is about 0.67. Great. And so these models are almost identical. across these different data sets. And so, if I were just to be going by these metrics and thinking about running a model, linear model on this data, I would be pretty happy, right? Good statistical significance, pretty high R squared. Okay, let's continue on. Let's look at model 3. Same story, about 0.5, significant to the 1% level, R squared of 0.67, and probably, as you can guess, my model 4 is the same thing here, significant again to the 1% level, estimate of 0.5, and R squared here. Okay, so let us jump straight to the punchline. Okay, this is such a bad plot. Here we go. These are the data points in the Anscombe Quartet. And you can see that there are pretty distinct differences between these data sets. So this one, we might say, okay, not linear. This one has a big outlier on the y-axis. This one has a big outlier on the x-axis. And this particular data set has been specially manipulated to produce these results. But I think the point of showing this is that, the metrics of models of model success that a lot of people often rely on are not necessarily the best ways to interpret the fit of the model, and that even doing simple things like looking at your data are really crucial to getting to the success of the model. So hopefully at a high level, this sort of points out some of the issues with the common ways that people think about regression in terms of statistical significance and R squared. These are not the end all be all of getting good model fit. They mean really particular things. And we shouldn't extend our interpretation of what standard errors and R squared means beyond their actual sort of statistical definition. Okay, so I'm gonna sort of end on this note today, and we're gonna dive much more into detail about linear regression in the coming couple classes. Sorry, I'm a little bit over time today, but again, I'll stick around for a couple minutes in case anyone has any questions. Otherwise, I will see you guys next week. If you didn't see the announcement on course logistics, there's a couple things. So the assignment has been posted, and I pushed back the due date. Thanks for the reminder from last time. And then my office hours are going to be held on Mondays in the late afternoon. Those details are posted on Canvas, and it's going to be on Zoom, so there's a different sort of Zoom meeting, and the link is available on Canvas as well. Okay, so I'll see you guys next week, and I'll take any questions that people have, but feel free to trickle out now.
Thanks, Alan.
Yep, no problem.
Hey, Alan, I had actually like an administrative question.
Yeah, absolutely.
So yeah, I emailed you last week about this, but so I'm that class that overlapped with this class. I like ended up dropping it, but now I'm like reconsidering taking it. And so I think what I'll have to do is like drop this class, waitlist on that, and then get a PTA for this class. And so would that work for you?
What's a PTA?
I forget what it stands for. But
let me hang on. Let me stop the recording because
okay.
yeah, they don't need to.